Hello everybody. My name is Yordan Karadzhov. I'm working for the VMware's Open Source Technology Center. And in this talk, I'm going to tell you about how you can use tools which have been originally developed for doing big data to look into the Ftrace data. That's my first time speaking at Plumbers, so maybe I have to introduce myself. The interesting thing about me is that before joining VMware's open source team, I used to be experimental physicist. So maybe this is not going to be the typical presentation of a software engineer. I hope you like it. OK, so just before starting, let's say a few words about the motivation for doing this work. So first, Ftrace, that's the official tracer of the Linux kernel. I'm not going to explain this. The question is the Ftrace data big data? Well, not necessarily. In most of the cases, no. If you know very well what you are doing, and if you have a well-defined question, actually Ftrace can give you a very short answer, and it's not a big data at all. But it's a sophisticated instrument. There is a large variety of ways you can use it. So let's say that you have some non-trivial or maybe a very specific for you problem, and you don't know exactly what's going on. You have recorded a lot of tracing data. So the question is what to do now. So far, we've been answering just use KernelShark to look into this data and to understand what is going on. So I'm not going to explain KernelShark here. If you want to know more about KernelShark, Steven gave a very good presentation at Open Source Summit North America just a month ago. There is a video, I believe. Or there are many videos on YouTube about KernelShark, so I'm not explaining this thing. But in this talk, I will actually, so just to step back, I'm the commentator of KernelShark. I'm actually the main developer right now. But in this talk, I will tell you that the KernelShark GUI has some weaknesses, and actually, you can do much more if you go behind this GUI thing. So this one slide, which I took from Steven's presentation from Open Source Summit North America. In this place in his presentation, he explains how you can actually see what's going on with the real-time system. The real-time system is supposed to run RT tasks with high priority for 95% of the time. And then for 5% of the time, give the chance for a low priority tasks to run if there are any. So here, he clicks at the end of this period with marker A of the GUI. I don't know if you see the marker here. So he clicks here. Then he selects the right event, clicking here. Then switches to marker B, selecting the right event here. He measures the time interval. Then he measures the time duration of the void, the small gap, and he concludes that everything is OK because you have exactly 95% of the time being spent running RT tasks. But the point is, this is a lot of clicking. And in the same time, is this really enough to make any conclusions? Because we just randomly zoomed in very deeply in the data in one particular place, which was completely randomly selected. We saw that everything is OK here, but is this really enough to make any conclusions that the system is operating as it should, that everything is OK everywhere all the time? Oh, I would say no. So now imagine doing the same thing 10,000 times. Well, this was it's just not doable. I mean, you can't approach a problem like this with the GUI. It's just not possible. There must be a better way of getting this job done. And yes, I think there is a better way, which is a complementary. And imagine having something like this. So you load a Python module in Python, KSharkPy. Then you open your data file. Then you load your data. And then you loop over the data. So that's not a real code, of course. I'm just trying to fix the idea. But so you select your event A. You select your event B. You measure the duration between those two events. You store this information. When you finish looping over the data, you do some calculations that you may need for your analysis. You plot some summary of the results. and eventually you can even draw some cool histograms or graphs which you can put in your presentation. This can be, I think, by far more useful in this particular case, which Stephen was showing me in his presentation. So that's another stolen slide. That's a typical slide people using when they explain NumPy and how it's this great, powerful, and shiny instrument. So typically, the typical slide is the languages are given in the opposite order. They usually put the numerical or scientific programming languages first. So my contribution to this slide was to change the order. But the point is you have some languages like R, MATLAB, Octave maybe, which are just designed to do mathematical calculations. They are very optimized, but are not very useful outside of this scope. And you have the general purpose languages, of course. And when you combine the two, general purpose language like Python with scientific computing, you get NumPy. That's the idea behind developing NumPy. What's the important thing here? So NumPy is not part of the Python language. It's just a library. It provides n-dimensional arrays of homogeneous type. So you have strong typing of your data, which makes everything run fast. NumPy also provides you with a large collection of mathematical functions which are operating on top of this array. So you can do many different things. The other nice thing is that if you have a C or C++ or Fortran code, you can easily integrate this with NumPy and just use it. Also, you have some complementary packages like matplotlib, which you see how we use this to plot histograms. You have a SciPy library, which adds things like optimization, for example, linear algebra, integration, fast Fourier transformations, and things like this if you need this. So many NumPy operations are actually implemented in C, which is good. In fact, the NumPy arrays, the way they are defined is very similar to the way we know the arrays in C. And the cool thing is if you have a C code which allocates a memory for an array and fills this array with data, then you can just wrap this thing into a NumPy array. You don't need to copy any data. I mean, you create your NumPy array directly from your C array. So let's see how we can take advantage of all this thing and eventually get our tracing data in Python and start analyzing in there. So we'll take advantage from something which I would say almost exists already. Even with KernelShark 1.0, if you take the code and build it, you get a library which is called libkshark. We don't call this an official library because the API is still not completed. We try to get a good API from the first attempt, but we are still changing a few things. So the library will become officially available with KernelShark 2.1, which is
2.1 or 2.0?
2.0, yeah, sorry, 2.0, which is under development right now. I'll be giving a demo talk at Open Source Summit Europe in Lyon. So if you are interested, come to see this talk. It will be particular for KernelShark 2. So the KernelShark 2 will include the final version of, or not final, but the official version of the library. But the library is still there even with version 1. And for a proof of concept like this one can be used. So together with the version 1, if you get the code from kernel.org, inside the KernelShark directory, there is another directory called examples. And in this examples directory, we have a collection of very simple C programs which are there to demonstrate how to use the library. And that's one of these examples. Actually, it's not the whole example, but I wanted to somehow get the code shown on 2 slides, so I removed a lot from the code. But the idea is it's as you can see, it follows the same sequence of instructions that we saw in our Python code, which we would like to have. So you basically just initialize the session, you open a file, then you load the data. Again, this part here is not a real code. That's just to fix the idea that you loop over the data. The difference compared to Python is, first of all, you have to clean up. That's your responsibility. Here in C, you can print the summary of your results, but unfortunately, there is no easy way to draw histograms or graphs or things like this. That's a weakness. So just to summarize, this proof of concept NumPy interface to access the Ftrace data in Python via NumPy arrays is nothing more than just a tiny wrapper around this library which KernelShark provides or will provide with version 2.0. And so enough for explaining. Let's see some example.
So one question.
Yeah.
So could you do something, hook into print dot, graph viz with the printing statements from your program?
In C, you mean?
Yeah.
Yeah, you can do this, but I mean, you have by
could
far
generate-
more sophisticated and user-friendly instruments for drawing histograms in Python, and you can do much more.
I think I mean, preferably, I'm a C programmer. Yordan likes Python. So, but a lot of people, it's like anything with the simplicity of Python is there. I mean, you got a lot of tools.
Well, I think when you see the example, you understand why we want to use
Yeah, that's
Python.
fine. I thought you were trying to use you have a C program to begin with. Never mind.
Yeah, well, basically, I think what you're saying is we have the code that we have is written in C.
Yeah, so under the hood, everything runs in C. I mean, the Python is just a tiny wrapper around the C library.
Yeah.
So the first example, with this example, I'm trying to reproduce the original study done by Wolfgang and Daniel. They presented this at the Open Source Summit Japan this year. So the goal is just to reproduce the study that they did for the real-time, for the latencies of the real-time system with the new instrument, and eventually show you or convince you that the new instrument can give you more opportunities, and eventually it's more powerful and can help you understand deeper what's going on.
Actually, I think they did a talk here on Kernel Summit on the first day.
Maybe, okay. So the goal of the analysis is to get a statistical estimate of the probability of exceeding the worst case execution time, or to explain simple, just what is the probability of having a very large latency when you run your application. And yeah, once again, I want to remind that this is just a demonstration of the instrument. The whole credit for the analysis itself and the idea goes to Wolfgang and Daniel. So they're using Jitterdebug to study the latencies. It's just an implementation of the so-called psychotests or psychotest. Yeah. The idea is you have a task which runs on each CPU, which is doing a very simple thing. It initializes the high resolution clock, resets it to 0, and then goes to sleep for 1 millisecond. When it wakes up, it gets the time of the clock, resets the clock again, and goes to sleep again, and you repeat this infinite number.
It doesn't actually reset the clock. It actually just wakes up at every millisecond. It's like
yeah, but you have this high resolution
oh,
time start.
No, the reset there that you see is that's a kernel inside code. That's actually the kernel reset timer. It's it's slightly different than what the actual application's doing. You look at the kernel level.
But the point is we don't use this clock anyway because we use the timestamps of the events. So you can't see this thing here because you have to zoom. So this is the next slide, just zooming in one of the executions of this cycle. Here in the beginning, you see the the scheduling, when the task gets scheduled. The first thing is this print event, which we just use to get the timestamp when the execution of the task starts. Then you have this init start, and basically from the start, we want to go to the next, to the print event in the next execution and measure this duration. So it's expected to be 1 millisecond. So everything that is more than a millisecond is latency in this experiment. And going back here, so here with the GUI, we've measured that the latency is around 300 nanoseconds. So very small latency. Looks great, but the problem is it the same everywhere? So we will do a statistical analysis, and we'll try to estimate the probability of actually having much larger latencies. And to make it more interesting, together with Jitterdebug, we will run Hackbench, which is a stress test for the scheduler. So the system will be really heavily loaded when we run this. So how we are going to estimate the probability of having a large latencies? There is a special theory in this, which is part of the statistics, which is called the extreme value theory. Usually in the textbooks, when people are introducing the theory, they use examples with precipitation or water levels of the rivers, because when the theory was developed back in the 19th century, the motivation for developing this was to build infrastructure for preventing floods, protecting the population from floods. And in many books, that's the way actually the math gets introduced. So I will follow this tradition. Here you see data series of precipitations per day, like millimeters per day. And you see you have some extreme values, but most of the case you have rain which is around 20 millimeters per day. So the way this peak over threshold approach to the problem works is you just ignore all the data that is below the threshold. You don't care about this data. You take only the data which is above this threshold. And now imagine projecting all these red points here that you see on the diagram on the y-axis. This will form a histogram for you. And here in this bin of the histogram, you will have a lot of points, I mean, a relatively big number. And when you go to the higher, more and more extreme values, you have less and less data. Okay? So how can you build a model on top of this thing? That's the so-called generalized Pareto distribution. It's just a function which is very flexible. It has three free parameters which you can tune. And with those parameters, you can get very different shapes. On the right side of the slide, you see how this function looks for different values of the parameters. Just to explain a little bit more, so if this function has to describe a probability, so all the area that is below the curve must be equal to 1, because the total probability of having any value for the latency or any value from the precipitation should be 1. Yeah? Makes sense? But well, you may ask yourself, see, I clearly see that the red line covers a much bigger area than the blue one. How they can be equal? Well, it's very simple, because this large tail, which goes outside of my slide here, continues almost to infinity eventually. And the tail of the red line vanishes very quickly and becomes negligible, while the blue line has a tail which goes much far. And at the end, the two areas will be the same. Going back here, so we have data for just, what's this, 11 years. Imagine having the data for the entire history of the planet Earth. Well, maybe then you see a precipitation which goes to infinity. I mean, if you have an infinite amount of data, your data must be described by some distribution like this one. So going back to the problem that we are trying to solve, here are the latencies that we observe in our test. Here on my top left plot, you see the histogram latency. So the y-axis is logarithmic, just to be able to see better that we have two latencies which are around 30 microseconds, so significant latencies. In the example which we saw with the GUI, we saw 300 nanoseconds. And here we see 30 microseconds, so it's a significantly larger latency. Below, you see how this histogram gets fitted with the theoretical distribution. See, the curve of distribution follows the histogram more or less correctly. That's the result of your fit, the estimate of the parameters of the distribution. This one has a 15% error. This one has just 3% error. This one is fixed because we know that we are cutting at 10 microseconds. And the goodness of the fit is more or less correct. I mean, perfect fit will give you 1. Everything that is much smaller than 1 is very suspicious. You probably have a bug in your code if you get such a value. 1.8 is a decent fit. So having this thing, we can now recalculate the probability. And the probability is calculated with this so-called return plot. So let's say you're asking yourself, what is the probability? So how often should I actually observe in my data a latency which is around 30 microseconds. So you just take this red line, then you find here that you should expect to observe such a latency more or less 1.5 times 10 to the 6, which is 1.5 million, once every 1.5 million iteration of your cycle test. And this is more or less what you see here, actually, because the entire number of cycles that we have in the data is 2.5 million. And we see two latencies like this one. Well, you may ask yourself, well, it's not exactly correct. It gives me a number which is kind of less of what I see. That's because the model is actually trying to see the entire picture, not just looking for the 30 microsecond latencies. He also takes into account the part that is here. And because you actually don't have a lot of events in this case, it kind of thinks maybe I'm just very unlucky to have two 30 microsecond latencies in my data sample. Okay, if you compare the performance between the case when you run Hackbench and the case when you run on an idle machine, you see actually there is a very significant decrease in the performance. This thing on top is your probability estimate for the case when you run Hackbench, and this below is your probability estimate for the case when you run Jitterdebug on an idle machine. So really running Hackbench results in a significant decrease in the performance of the system.
Actually, it's more not performance, but latency, jitter.
Yeah, okay. Okay, so let's see how all this thing was done actually in this Python code. So that's my second example. So the entire script is, let's see, it's like 300 lines of code, but I have a lot of comments. So it's a very simple script that does all this thing. So it starts here. We open the file. We are loading one plugin, actually. Here, I didn't explain anything about plugins, but yeah, we load one plugin. Then we load the data. We find the ID of the high resolution timer start event. We find the ID of the print event. Then we find the PIDs of the old threads of the Jitterdebug program. Then we iterate over each task. This is basically per CPU data. Here we calculate the total probability, and the place where we actually fit the histogram with the curve is here. It's this part. Here we plot the legend that you saw in the plot, and here we're just doing some plotting. I mean, this creates
Can
you
you post,
this plot.
is that example anywhere, or can I get post so that people can actually download and take a look at it?
Well, it's not posted right now. The whole development goes on the Linux Trace Devel mailing list. Some previous versions of the NumPy interface have been posted there. This one will be probably available in maybe a week, because I still have to clean some final.
I'm not talking about the NumPy interface. I'm talking about the script you use.
Well, the examples will be part of the interface. I mean, they will come together with the interface. Yeah, all the examples. Okay, so far this basically just reproduces what Wolfgang and Daniel did. So what is the complementary thing that our instrument can give you? If we go back to the code of the example, at some point we have this. Here we are creating a JSON file which actually gives the description of the KernelShark session. It's a very simple file. Here we just put the PID of the process that we want to see, on which CPU it runs. Here, so we take the start event, we take the stop event. We just add a little bit of margin to the two sides of this time window. So, and we set, saying to the model of the KernelShark, okay, visualize for me this time window. Just zoom around this very large latency which we discovered, and make me a session that will show me this thing. So a session file looks like this. It's a very simple human-readable JSON file. You have the description of your model. So starts from this time. This is the timestamp of the first event that will be shown. Go to the end your time window with this timestamp. Make me 1,000 bins. Set the marker B to be at the start. Set marker A, or it's the opposite. Set marker A to be at the start. Set marker B to be at the end of this big latency.
Can you explain what bin is?
Explain
what a bin is.
Bin. Well, that's okay. I can explain what is bin. So the model that we use to visualize the tracing data is based on this concept of binning. So because there is no, if you have in the case of this Jitterdebug test, we have hundreds of millions of trace records. There is no way to visualize this with the limited amount of pixels that you have on your screen. So everything that, so we just separate the whole duration of the data in time into small sub-intervals, sub-time intervals, which are uniformly sized. And everything that goes into one of these sub-intervals or bins gets visualized by a single graphical element, which is like a tick here in this graph.
1 pixel.
Yeah, 1 pixel is 1 bin, essentially. But the point is, the way we define the bin is just a time interval inside your tracing data. Okay, so we have our session descriptor file, which has been generated by the Python script which analyzes the data. And now we can just do this KernelShark minus S, your JSON file, and it will directly zoom and show you the place where this very big latency is happening. And strangely, you see that the task is waiting for like a 37 microseconds without doing anything. So our current explanation for this is that there is a SMI going on right now. but we are investigating this thing. But the point is, you can really connect the scripts with the GUI, and what has been discovered by the script can be eventually seen in the GUI. You can investigate what's going on. You can get a deeper understanding. So the two instruments are made to be complementary, not used standalone, but together. Okay, this example is not very good for making demo because, I mean, to accumulate enough statistics, you need very large file. In this case, the file is like 10 gigabytes. And running the script takes several minutes, so it's not good for a demo. I will show you something which goes quickly for my demo. Okay, so I have a hello world executable here, and I'm going to record tracing data for this executable. In particular, I'm interested in page faults. So I want to record all page faults which are happening when I start this hello world program. I will need to map the memory of the process, so I need to know the address space of the executable. And basically that's it. So here it's very simple command. I'm saying trace cmd record minus, so I want to exceptional events. That's where the page fault events are. I want to map to get the address space of the process, and the output will be trace underscore pf.dat. And I'm running this hello world executable. Okay, hello world. And here's my data. So now I will run a script which looks like this. Basically, I'm doing the same iteration over the data, looking for page fault user events. For each event, I'm getting the offset and the IP, and then I will use GDB to tell me what's actually at this address. And I'm doing this thing here. I'm just running GDB in bash mode with this command here. And then I'm parsing a little bit the output, and I'm putting it into a table, which is like a chart, the places where you get the most page faults. Okay, so let's run this. So it's a very simple program. So apparently you don't get a lot of page faults. But yeah, so you have 3 page faults from here. So that's in LD. What else? Well, all page faults are basically from here. So let's do something a bit more interesting. So instead of running with this hello world program, we will start Firefox. Yeah, so we have to do a little bit of more. So -F. I don't want to run Firefox as root, but if I just do this, it will attempt to run Firefox as root, and Firefox doesn't want to run as root. So I will say -user Yordan. Okay. I mean, it's no magic here. I'm just running Firefox with my normal user, not as root.
Just FYI, the options, the proc map, and the -- user, that's still in. I don't think I've merged that upstream yet. The patches are out there. I don't think we.
Yeah, the patches are there. They're not
I've been
upstream.
late into merging that. That will be.
So Firefox is starting. I don't know why I'm getting these warning messages. I mean, if I just start Firefox, I'm not getting this. It shows up only when I'm tracing.
I'm wondering if that dcache you somehow created it and it created it as root or something.
Maybe, yeah. And so now running the same script on the new data file. Well, see, so you have like 1,100 page faults from this memory location here, which is something inside libc, and then you have 600 page faults from here. I mean, yeah, apparently Firefox creates a lot of page faults when it starts. Okay, that's all. If you have questions.
Have about 9 minutes for questions.
Right, not necessarily a question, but more comments. So I'm one of the maintainers of a tool called Lisa, which is doing exactly that in terms of using Python to analyze trace outputs. And we actually use that to mostly verify what's going on the shell. So I work for ARM, so we care about stuff like big. LITTLE and placing, doing weird task placement because we have this weird architecture. But so the thing what we're really missing is what you're introducing, which is a nice interface in Python to access data from the recorded trace data. Because right now what we're doing is quite ugly, is we pass the output of TraceCMD in text format, which is human readable, so it's not made for machines, but just someone wrote that and we've been carrying that over for quite some time. So I'm really interested in using that new interface. But for the analysis part, maybe I can give you a demo at the break, but we have a lot of interesting analysis stuff like wake-up latency, heat maps. Yeah. We've been building like a library for the past 6 years, so we have a lot of that.
Could you please join Linux Linux trace devel at vigor.kernel.org, and
I saw that thing on that list. So
yes, so please, I mean, this is all under development. We could use, we want to make it.
It's in a very early stage of development right now.
Yes.
So I mean, any help, any advice, anything is more than welcome.
And also public service announcement. I have some issues with some people who are saying that because we are doing this in Python, performance is going to be horrible. NumPy is mostly done in C, and if you do it right, you will get decent performance. So as an example, I had someone complaining, I have this 300 megabyte trace, and I'm using this analysis function in library. It's taking 45 seconds to process. I give up. I'm going to rewrite your thing in C++. It's going to be much better. I took an afternoon to rewrite the thing, and it passes in 500 milliseconds. So you can have decent performance with Python if under the hood you don't have Python, which is what NumPy is all about. Yeah.
So. Well, you have to have certain awareness of what you are doing, because even if you use NumPy arrays, you just try to stick with strong typing. I mean, don't add your own lists. And I mean, for example, when you loop over data, you record into something which is list. If you expect more than 1,000 entries to this list, just switch to NumPy array. I mean, just keep in mind what has a strong type and what doesn't. That's what makes Python slow. I mean, even if you use NumPy, if you are not careful, you may still have a script which is very slow.
That's what stupidly iterate over the data.
Yeah.
But they have good documentation. You should not be doing this if you care about performance. So just follow the documentation.
Absolutely. Yeah.
Just to get my head around some use cases. So imagine I use Ftrace to record, TraceCMD to record a bunch of different events. Could I use this to then have tools that work on that capture file? For example, could I re-implement vmstat and say run vmstat on the capture file so I can see similar metrics? Things like that.
I mean, this is all library. So yes, I mean, you have all the access. I mean, I don't know how much you have to work on it, but this is all becoming a library. I mean, the libkshark.o, everything you saw in Python, I believe there's a C interface as well.
Yeah. Actually, the C interface is richer. I mean, the Python is just a minimum useful thing. You have much more options in the C, using directly the C interface.
So, I mean, exactly what are you looking for? I mean, you could do basically any data analysis you want.
It's the use case where you want to do a black box recording and then afterwards create a bunch of tools to analyze it in different ways you didn't think of at the time. With BPF real-time tracing that I do, if I don't think of tracing something, it's gone. But with black box recording, I trace a bunch of events, and then afterwards I can think of a new tool or a new analysis technique.
Yes. Yeah. I mean, if you have the data in there, and just the trace.dat file there, because that's actually something that happened was I had a trace.dat file, and I went, wait, if I look for these things. Like, I didn't even think about it when I did the record. I just recorded a bunch of events and everything. Then later I said, wait, I need to analyze like some, it was like, I don't know, it was a wake up or something like that, or some path of like, I wanted to follow like interrupts going up and saying, where was this happening? I just wrote a script that, well, I used libtrace event just to attach to everything and read the data and just do my analysis at a later time. So, I mean, the data's there, you can do whatever you want with it once you have the data. But you can't go back and say, add more data to it after recording's done.
Okay, that makes sense. Thanks.
This is all
Maybe
part of it.
if I can add something. Basically, you may have two different approaches. And the first thing is, I know what I'm looking for. I'm very confident that I understand what's going on. So I will record the minimum amount of data that will answer my question. This includes, you can do, online processing of your data, like what the histogram code in Ftrace is doing. So you directly calculate fill your histograms when you record. And everything that is not related to your histogram, this data is just lost. But because you are confident that you know what you are doing, you don't care. But if you don't know what you're doing, another approach is just record as much as you can, and then you figure out what's going on with all this data. Of course, in this case, it's not that efficient. First of all, you create a lot of data which most probably is just useless for you. Also, you have this Heisenberg problem that, because you do a lot, you actually change the thing that you're trying to observe. Maybe I think that this approach is good for prototyping, just to understand what's going on, to get an idea, and then you probably go to another approach where you record less and you are more efficient.
Yeah, well, I mean, you do the record. What I usually do is I'll do like a record everything, and then say, oh, there's a lot of this stuff I don't care about, and just turn all those off, and then do the record again. That's been very useful.
So we have last question.
Regarding the libKShark, have you considered making an input plugin for libbabeltrace? Because we are talking about unifying the trace format, and instead of having to create yet another trace API. I'm curious if you looked at that.
Yes, absolutely. Actually, that's one of the reasons why the library is not officially called a library yet. That's one of the weaknesses of our original API, because we wanted to have the input, data input abstracted, so you can actually fill the model with just arbitrary data format. But yeah, it turns out that with the first version of the API that we implemented, there are problems doing this. So that's one of the reasons why we are modifying the API right now. But yeah, with the new version of the API, which will be in KernelShark 2, the input is completely abstracted, and you can merge different inputs. So you can have one tracecmd, that trace.dat file. You can merge this thing with a babeltrace data file. Actually, because VMware has, they have their own tracer for the hypervisor, which records in a completely different format. And we want to merge this, the data from the hypervisor and the guest together. And I'll be demonstrating this in Lyon. So yeah, we have to merge different data formats, and this works.
Real quick.
Once you've got the universal tracing API, how long until you have the universal tracing library done?
Hopefully we get
It's the follow-on.